Our next lesson in our bonding and intermolecular forces unit is on the drawing of Lewis structures, or dot diagrams, which we use for covalent compounds. Taking a look at our learning standard and targets here, we are working on modeling and describing chemical bonding. And this particular video will focus on the second learning target. We want to be able to draw dot diagrams to model bonding. So Lewis structures, or dot diagrams, are diagrams that we draw to show the bonding that occurs typically in covalent compounds, and thus that's what our video here will focus on. Just an example of what a Lewis structure is and the notation that we will see. So Lewis structures, they show the arrangement of electrons in covalent compounds. So when we talk about electrons, remember with chemical bonding, we're talking about the valence electrons. So it's the only electrons that we are concerned with. We will see shared electrons, because after all, remember, covalent bonding involves the sharing of electrons between atoms. And we'll also see lone pair electrons. These are the electrons that are not being shared, that belong to just a single atom. So here is an example of a simple Lewis structure, or dot diagram, for water, H2O. So notice we have the two hydrogen atoms and the one oxygen atom. And then the lines that we see here between the hydrogen and oxygen, each line in a Lewis structure represents a shared pair of electrons. Note, it's a shared pair, so each line is 2 electrons. So this line here between the hydrogen on the left and the oxygen is 2 electrons. And the line on the right between the hydrogen on the right and the oxygen is also 2 electrons. So the hydrogen on the right and the oxygen are sharing 2 electrons. The hydrogen on the left and the oxygen are sharing 2 electrons. The dots represent lone pair electrons, and we do talk about them in pairs. We will typically draw them in pairs like you see here. So notice in total here, oxygen has the 4 electrons for itself, the 2 lone pairs for a total of 4 electrons there, and then the 4 electrons that it's sharing. Remember, each line is a pair of electrons. So that shows oxygen has an octet with its 8 electrons. Again, the 4 for itself, the 4 that are being shared. Now notice the hydrogens only have 2. And remember, that's quite all right with hydrogen, because hydrogen just has 1 energy level. So for it to have a full octet, it only needs 2 electrons. So this will be a common theme as we learn how to draw these Lewis structures, and how we know where to put hydrogen and how many bonds it's going to create. So let's just jump right in here and take a look at how we go about drawing these things. There are a series of rules for drawing Lewis structures. I will just present the rules as we go through an example. The first example here, we'll be drawing the Lewis structure for chloroform, which has the formula CHCl3. So it'd be 1 carbon atom, 1 hydrogen, and 3 chlorine atoms. So the first rule is to do this, to determine the central atom in the molecule. What atom are we going to put in the middle? Most molecules will have a single central atom. We will see some examples of molecules that have more than 1 central atom, but in these simple cases we'll start with just a single central atom. So here are some guidelines for helping us determine which of these atoms will be in the middle. First of all, molecules often have symmetry. In other words, if we were to cut them down the middle, they would be the same on either side. Molecules often exist this way. Not always, as we will see, but that's often a good starting point. The least electronegative atom is usually the central atom. Not always, but usually. Again, this is a very good place to start. So I can look at the electronegativities of these elements, carbon, hydrogen, chlorine. I can look at which one is the least electronegative and have a pretty good guess about what my central atom is going to be. And then here is a rule of thumb that is always followed. Hydrogen is always a terminal atom. Terminal meaning on the end. It's never in the middle. It's never a central atom. And this goes back to what we said on the previous slide. Hydrogen's only going to form 1 bond. It only needs 2 electrons. So it's only going to share 1 pair. There's no way you can put it in the middle, because it would always have to share at least 2 pairs, and hydrogen's never going to do that. So combining all of these ideas, here is the central atom in our molecule. It would in fact be the carbon. Okay, if you think about each of these rules of thumb here, I take this molecule and I cut it down the middle. Okay, if I put a mirror here going right down the middle, we would see it's the same on either side. It'd be a mirror image of itself on either side. Now, one thing we will learn later on in this unit is about the shapes of molecules and how these atoms aren't all going to be arranged in the same plane like we're seeing here around the carbon. But as far as drawing it on a sheet of paper, this is what it would look like. Now, whether you put the hydrogen on top or on bottom, or you could even put the hydrogen on the left or the right, it would still be the same structure. Because imagine the hydrogen being over here on the right. If I were to cut a line or draw a line going right through the middle, right to left here, it'd be the same on either side of that line. Okay, so no matter how you draw it, carbon's going to be the central atom. You have 3 chlorines arranged around it and a hydrogen as well. Carbon is the least electronegative, and then hydrogen, as we said, cannot be a central atom. You can never put hydrogen in the middle. It has to be on the end, or not in the middle, as we're seeing here. All right. Step number 2, determine the number of electrons available for bonding. This just means we're going to count all the valence electrons from these atoms that we have here in the molecule. Now, something that's not going to be of concern here is if we had an ion, something that had a positive or negative charge, we'd have to add or subtract electrons for that. Not a concern here because this is not charged. And then once we do know the number of electrons, we want to figure out how many pairs of electrons that is, because we'll often think about the electrons in pairs, not as single electrons. So going through the counting here, carbon has 4 valence electrons because it's in group 14. Hydrogen has 1 valence electron because it's in group 1. And then chlorine has 7 valence electrons, but I do need to multiply that by 3 because there are 3 chlorine atoms. So if I add all those up, 4 plus 1 plus 7 plus 7 plus 7, that's going to give me 26 electrons that are available for bonding. Or in other words, that is 13 pairs of electrons. So in other words, when all is said and done with my diagram, I have to have 13 pairs of electrons or 26 electrons on this diagram, no more, no less. If it's any more, any less than 13 pairs, my Lewis structure would not be correct. All right, the next step. We now want to place single bonds between the atoms. And as we do this, we want to keep track of the electron pairs that we have for our molecule. And remember, each bond is 1 pair of electrons. Each bond is 2 electrons, so every bond is a pair of electrons. So if I put in single bonds here, I'm going to bond each atom to the central atom, like so. So I put in 4 bonds, and recall each line represents a shared pair of electrons. I just used 4 of my 13 electron pairs, so I'm going to subtract that from my 13. So I have 13 electron pairs minus the 4 bonding pairs I just put in. I now have 9 pairs remaining. So I have 9 pairs left to go on my Lewis structure. My next step is to place the remaining electron pairs on the terminal atoms to fill the octets of those terminal atoms. So remember from the previous slide, I have 9 pairs of electrons left over. And my rule tells me I need to take these 9 pairs and distribute them on the terminal atoms. Remember, those are the atoms that are not the central atoms, to fill their octets. Well, remember, hydrogen can only form 1 bond. It's never going to have any lone pairs because that 1 bond is 2 electrons. Remember, it counts for both the hydrogen and the carbon because it's being shared. Hydrogen has a full octet with just those 2 electrons. So the hydrogen does not need any of these 9 pairs. The chlorines, however, they are going to need some electrons. If I just think about the chlorine here on the right, I've added 3 pairs, or 6 electrons in total, 3 pairs of electrons. So there's 6 electrons it has for itself, plus the 2 electrons that it's sharing with the carbon. This chlorine now has a full octet. So this same thing could be said of the other chlorine atoms, where each of the chlorine atoms will need 3 pairs of electrons. So now the chlorine on the left has a full octet, the 6 electrons for itself, plus the 2 that are being shared. And then the chlorine on the bottom also needs 3 pairs of electrons, same reasoning. And notice we have now added 9 pairs of electrons, 3 pairs on each of the terminal chlorines. I've used all 9 remaining pairs, so I have no pairs left over. In other words, I cannot add any electrons, I cannot take any away. I am done adding electrons to my diagram. All right, step 5. Any remaining electrons after filling the octets of the terminal atoms go on the central atom. Well, in this case, we used all of our remaining electrons. We don't have any pairs left over. If there were any additional electrons, though, if I had any pairs left over, they would go on my central carbon atom. But I don't have any, so they don't go there. And then finally, step 6, if any atoms do not have an octet, rearrange lone pair electrons to form multiple bonds, in other words, double or triple bonds. We'll see an example of that in our next example, to fill the octets of all the atoms. So here, this step is not necessary because every atom has a complete octet. Remember, the hydrogen just needs the 2 electrons, so the 1 shared pair is good. Each of the chlorines has 6 electrons for itself, plus the 2 that are being shared with the carbons, there's 8. And the carbon, the central carbon atom, has 4 pairs of shared electrons, so 2, 4, 6, 8. It has its octet. Every atom has a full octet. There is nothing additional to do here, so there's no reason to rearrange the electrons. So our Lewis structure is complete as we have it drawn now. All right, let's look at one more example. This example is for acetone, CH2O. This is the primary ingredient in nail polish remover, so if you're curious what that is, that's what's in nail polish remover. It's acetone. Okay, so just going through each step like we did before. Our first step is to determine the central atom. Pause the video, look at the formula, see if you can figure out what the central atom is. All right, by examining the formula here, we can observe that the 2 hydrogens we know cannot be the central atom because they have to be terminal. The carbon or the oxygen could go in the middle based on symmetry. If you put either of them in the middle, you would get a symmetrical molecule. What gives it away is the electronegativity. The carbon has a lower electronegativity than oxygen, so we're going to put carbon in the middle. So your atom arrangement might be something like this. Again, exactly which side you put the atoms on really doesn't matter. You could put the hydrogens more down here to form more of a triangle looking shape. And we'll talk more about shapes of molecules in the coming lessons. That'll be of a concern to us. And for now, just making sure we get the correct basic arrangement with the correct central atom is good enough for now. All right, step 2. Determine the number of electrons available for a bonding. So again, pause the video, count the number of electrons we're going to have available for bonding. So recall that the electrons available for bonding are the valence electrons. So I will just count those. We have 4 valence electrons from carbon, is in group 14. We have 1 valence electron for each hydrogen, but I need to multiply that by 2 because I have 2 hydrogens. And then I have 6 valence electrons from oxygen because it's in group 16. I add all those up. That's going to give me 12 electrons or 6 pairs of electrons. Again, it is very useful to think of those electrons as coming in pairs. All right, step 3, place the single bonds between the atoms. So go ahead and do this and think about how many pairs of electrons you will have left once you have those single bonds in place. All right, so placing our single bonds, we're going to place 3 pairs of electrons, 1 single bond between each terminal atom and the central carbon atom there. And counting up our electrons, I said I had 6 pairs available from the previous step. Subtracting my 3 bonding pairs, that's going to give me 3 pairs left over. All right, step 4. Place remaining electrons on terminal atoms to fill the octets. So pause the video, place the electrons where you think you need to, keep track of the electron pairs as you go. So as we discussed on the previous example, the hydrogen atoms never need any lone pair electrons because they have a full octet with just the 1 single bond. The oxygen, however, will need 3 more pairs in order to fill its octet. If I put 3 pairs there, it now has the 6 electrons for itself, plus the 1 pair that it's sharing, so the 2 electrons there for a total of 8. So that's all 3 of my lone pairs that are left over. So I have no more pairs remaining. All right, step 5. Any remaining electrons are placed on the central atom. Well, from our previous slide, we used all of our remaining electrons, so I have no electrons left. So I can't put any electrons on the carbon because there are no electrons left to put there. And finally, step 6, and this we did not see in our previous example, rearrange lone pair electrons to form multiple bonds to fill the octets of atoms if necessary. So notice our carbon atom only has 6 electrons right now. The 3 pairs it's sharing, so 2, 4, 6 electrons. It is short a pair of electrons. It does not have a complete octet. So now is where step 6 comes into play. We are going to rearrange one of those lone pairs from the oxygen in order to get carbon to have an octet by forming a multiple, or what we call a double bond, with the carbon. So one of the lone pairs on the oxygen will actually be a second bonding pair with carbon. So just visually here, I'm just drawing an arrow going from one of these lone pairs down towards this where we're going to put the bond here. What you will do is you will simply erase that lone pair. So even though you have 3 lone pairs there, just erase one of them. It really doesn't matter which one. Just erase one of the pairs and then draw in a second shared pair by putting in a second line here that you see. So we have 2 lines here between carbon and oxygen indicating we are sharing 2 pairs of electrons. In other words, we call this a double bond. Now notice if I count up the electrons now, the hydrogens have 2 electrons each, which is just what they want, the 1 bond, so the hydrogen's octet is filled. The oxygen now has the 2 lone pairs, the 4 electrons for itself, plus these 2 pairs, these 4 electrons are being shared, so 4 plus 4 is 8 for the oxygen. And the carbon now has 4 pairs, or 8 electrons, 2, 4, 6, and 8 here that it's sharing, so the carbon now also has an octet. So we can see here how we would get this idea of multiple bonds in order to get all the atoms having a complete octet. Alright, so just the 2 examples there. As we will discuss in class, the way that you get good at drawing Lewis structures is just to practice and practice and practice. So we'll be working on lots of different examples. There are more complex scenarios that were not presented in this lesson here, but as you get good at the basics and you start seeing those more complex scenarios, you will be able to do them just with that practice that we are talking about.